Because I want to talk about KL Coolback Leibler discriminant analysis, it is based on Coolback Leibler divergence. Let's just start by calculating Coolback Leibler divergence between first two normal PDF and then between two multivariate Gaussian distributions. So Coolback Leibler between two normal PDFs. For example, one of them is drawn from a normal distribution with mu, mean mu, and variance sigma, and sigma squared, and the other one is Q of x drawn from normal distribution m and s squared. So the Coolback-Leibler divergence between these two distributions is p of x log of p of x over q of x d of x, which is equal to p of x log of 1 over 2p sigma squared xp minus x minus mu over 2 smug over 1 over 2p squared x minus m over 2s2. These two goes, and then this becomes log of s2 over sigma 2 square root of this plus p of x minus x minus mu 2 sigma 2 plus x minus m squared 2s2 dx. This one is very simple, log of s2 by sigma 2 because it's constant, and this one is 1, and the second term is minus, you can write it as x minus mu squared p of x d of x. This is just a definition of sigma squared plus 1 over 2 s2 x minus m squared p of x d of x. So this is equal to 1 over 2 log of s2 by sigma 2 minus sigma 2 over 2 sigma 2 plus 1 over 2s squared x minus mu plus mu minus m p of x d of x. So I just add and subtract mu because this one is equal to 1 over 2 log of s2 over sigma 2 minus 1 over 2 s2 x minus mu squared p of x d of x plus mu minus m squared p of x d of x plus 2 mu minus m x minus mu p of x d of x. This one is 0, and this one is definition of this. The sum is 1, And finally you can write it as S2 by sigma 2 minus 1 over 2 plus 1 over 2 is squared sigma 2 plus mu minus m squared. And so the Coolback-Liebert divergence between P and Q, you can write it as this. S2 by sigma 2 minus 1 plus sigma 2 plus mu minus m squared S2. Now let's write the Coolback-Liebert divergence between two multivariate Gaussian distributions. So one of them is 1 over 2 pi. Now this is the determinant of sigma, and x is k-dimensional. So this x is k-dimensional, and x minus mu transpose inverse of sigma x minus mu. So you can write the KL divergence between P and Q as log of P minus log of Q. Expectation of log of P minus log of Q. And you know that this one is equal to expectation of 1 over 2 log of determinant of Q, determinant of P minus 1 over 2 x minus mu P transpose sigma P minus 1 x minus mu P plus 1 over 2 x minus mu Q transpose sigma x minus mu Q. And this is equivalent to log of sigma Q. And this is minus 1 over 2 expectation of x minus mu transpose x minus mu P plus 1 over 2 EP x minus mu Q transpose sigma Q minus 1 x minus mu Q. You know, this one is a scalar. Because it is a scalar, trace and expectation can be exchanged. And also note that trace of ABC, you can rotate the element. So it becomes trace of CAB, rotated again, trace of BAC. And I want to use a formula in the cookbook, in the matrix cookbook, to simplify this one. And the equation in that book is equation 380. And so this one was 16 and this one was... So using these two equations, we can simplify the second term as 1 over 2 expectation of trace of x minus mu P x minus mu p transpose and as I said, trace and expectation can be exchanged, so trace of EP x minus mu p x minus mu p transpose xp minus 1, and this is just sigma p. And so let's carry on. This is 1 over 2 trace of sigma p minus 1, so that becomes identity, and trace of identity, sum of that, it becomes k over 2. For the third term, as I said, I use equation 380 of matrix cookbook, and in that book, the equation 380 is that expectation of this one is equal to m minus m prime transpose a m minus m prime plus trace of a sigma. And x is drawn from m and sigma. So the third term can be written as expectation of x minus mu q transpose sigma q, x minus mu q equal to mu q transpose sigma q minus 1 mu p minus mu q plus trace of sigma q sigma p. So the KL divergence, as I said, between p and q becomes 1 over 2 log of determinant of sigma q, determinant of sigma p, plus term 2, which is minus k over 2, plus term 3. So finally, you can write KL divergence between two distributions, P and Q, which are two multivariate Gaussian distributions, equal to 1 over 2 log of sigma Q, sigma P, minus K plus mu P minus mu Q transpose sigma Q minus 1 mu P minus mu Q plus trace of sigma Q minus 1 sigma P. We can simplify it more by saying that if we could assume that Q is drawn from a normal distribution that has zero mean, and I is your covariance matrix, it is a diagonal covariance matrix, which means all of them are just variance on the diagonal part, so it can be further simplified to dKL of P. This becomes very simple. Mu P transpose mu P plus T sigma P minus K minus log of sigma P, determinant of sigma P. And so I've calculated the KL divergence between two multivariate Gaussian distributions, which is quite interesting and useful. But the drawback of using these parametric modeling for distributions is that you're just forced to some restricted distributions, and some parameters, just mu and sigma. You don't know the distribution of your data, and many times these approximations are wrong. That's why people use non-parametric approaches. The same happens in statistics that use non-parametric statistics. For example, kernel methods, those are some useful things, and they try to go beyond parametric modeling. For example, in variational autoencoder, which is another type of dimensional reduction, you have assumed you know the distribution and you want to find. So you have restricted yourself to some predefined distributions, and in general your distribution may not be normal. It could be skewed, it could have high kurtosis and skewness, and even higher moments. You don't know up to which moment it does not. It does affect your results. So that's why these are the drawbacks of using KL divergence. But in the next video, I will talk about how we can use Coolback-Leibler divergence in discriminant analysis. Because after all, in in discriminant analysis, you can think of it as a KL divergence of, for example, KL divergence as a measure of separability of two classes by viewing them as a probabilistic distribution of training data. So KL divergence could be used for discriminant analysis as well. But as I will show in the next video, it could lead to some non-convex function. Non-convex function have many problems because you have many local minima, and so you need to use some methods such as successive convex approximation, methods such as difference of convex functions, methods such as majorization, minorization if you have a minimization problem, or minorization, maximization if you have a maximization problem. So all of those methods are used to overcome the problem of non-convexity. And although we have formulated, I will show you that we can formulate discriminant analysis by Coolback-Leibler divergence, but you should be able to use those methods such as majorization, minimization, all those successive convex approximation to deal with non-convexity of your problem. For example, in neural networks, your problem is totally non-convex, and so even if you use stochastic gradient descent, most probably you are just using some local minima as your final answer. And because it's so interesting that in the context of deep learning and neural networks, nobody cares about majorization, minimization, and those successive convex approximations, and everybody focuses on stochastic gradient descent, and rarely, and for example, mirror descent. And they don't mention, or they don't explain these methods, such as successive convex approximation, and how can you change the architecture of your deep learning to overcome the non-convexity in a systematic approach.